Combinatorics, Lecture 18, Problem Session. Problem 1. Find the generating function for the number of partitions of a non-negative integer n into distinct odd parts. Compute the number of such partitions for n is equal to 20. Solution. In analogy with what we did during the lecture, let us show that the generating function for the number of partitions of a non-negative integer n into distinct odd parts is given by the following formula. So g of x is equal to the product over all I from 0 to infinity, and then the factor corresponding to I is 1 plus x to the power 2i plus 1. Indeed, the coefficient at x to the power n on the right-hand side of this formula is equal to the number of solutions to the following equation. N is equal to a0 times 1 plus a1 times 3 plus a2 times 5 plus and so on. And we want to solve this equation for some a0, a1, a2 and so on, where each ai is equal to either 0 or 1. And of course, this is exactly what we wanted. So this solves the first part of the problem. To compute the number of partitions of 20 into distinct odd parts, let us note that these distinct odd parts could be 1, 3, 5, 7, 9, 11, 13, 15, 17, and 19. So we need to find all subsets of this 10-element set such that the sum of all elements in this subset is equal to 20. As 20 is even and all our elements are odd, we cannot have a partition with only one part. So we need to start with partitions with two parts, and these are exactly pairs I, 20 minus I. And of course they should be ordered weakly decreasingly. So we have 5 such pairs: 19,1, 17,3, 15,5, 13 and 7, and 11 and 9. Again, as 20 is even, we cannot have partitions with 3 odd parts, because the sum of 3 odd numbers is an odd number. So the next thing is to consider partitions with 4 odd parts. So A, B, C, D, where A is greater than B, greater than C, and greater than D. Then, of course, C plus D should be greater than 1 plus 3, which is 4, greater than or equal to, and so A plus B is less than or equal to 16. So there are two obvious solutions. We have 9, 7, 3, and 1, and 11, 5, 3, and 1. So these two partitions work. And then these are the only partitions when we have parts 1 and 3. As soon as we take the next one, 11, 9, 3, 1, the parts add up to 24, which is greater than 20. Now, if we change 3 to 5 and start with 1, 5, so the partition 9, 7, 5, 1, which is the smallest one, adds up to 22, and this is greater than 20. So 1, 5, and so no bigger parts could work. So this says that for partitions with 4 parts, we have only 2 solutions. Of course, we cannot have partitions with 5 parts due to the parity reason. And next, the partitions with 6 parts. We take the smallest one, 1, 3, 5, 7, 9, 11, and the parts add up to 36, that is greater than 20, so this cannot work, and anything bigger cannot work. So we have 7 partitions of 20 into distinct odd parts, 5 of them with 2 parts and 2 with 4 parts. This completes solution of problem 1. Problem 2. Prove that for n greater than or equal to 0, the corresponding Bell number b of n equals 1 divided by e, sum over all k from 0 to infinity, k to the power n divided by k factorial. That's known as Dubinsky's formula. Solution. Let us recall that during the lecture we computed the exponential generating function for Bell numbers, and it is equal to e to the power x minus 1. So the exponent of x minus 1. Recall that the usual power series expansion for the exponent, so exponent of y, is the sum over all k, y to the power k divided by k factorial. If we plug in y equals to the exponent of x, we will get that the exponent of x equals sum over all k, exponent of kx divided by k factorial. So exponent of x to the power k is the same as the exponent of kx. And now we apply the same formula again now to exponent of kx and get a double sum. So sum over all k, 1 divided by k factorial, sum over all n, kx to the power n divided by n factorial. So this means that the exponent of x minus 1, so our generating function, equals 1 divided by e, sum over all k, 1 divided by k factorial, then sum over all n, kx to the power n divided by n factorial. And the Bell number b of n here is the coefficient at x to the power n divided by n factorial. And if we change the order of the summation, we can read off that the coefficient at x to the power n divided by n factorial on the right-hand side equals 1 divided by e times the sum over all k, k to the power n from here, divided by k factorial from here. And this completes our solution. Problem 3. Prove that the Stirling number Sn, 2, that's a Stirling number of the second kind, equals 2 to the power n minus 1 for all n greater than or equal to 1. And use this formula to derive a formula for Sn, 3. Solution. A partition of the set 1, 2, and so on n into two non-empty subsets x and y is of course uniquely determined by choosing x or y, because the other set should be the complement, and we have the condition both should be non-empty. The set 1, 2, and so on n has 2 to the power n subsets. And 2 to the power n minus 2 of these subsets satisfy the condition that neither the subset nor its complement is empty. So we should throw away the empty subset and we should throw away the whole set 1, 2, and so on n, because it has the empty complement. Note also that in a partition the order of x and y doesn't matter. So if we just choose a subset, then the complement is uniquely defined. But if we choose the complement, it defines the original subset, and so we get the same partition. So this means that the number of partitions of n underlined into two non-empty subsets is 2 to the power n minus 2 divided by 2, which is 2 to the power n minus 1 minus 1. And this proves the first part of our problem. Now to compute Sn, 3, let us denote it by an. N is greater than or equal to 0. Clearly a0, a1, and a2 are 0, and a3 is 1. And what we now do, we will now establish some recurrence for this an. Recall that Stirling numbers of the second kind satisfy the recurrence Sn, k equals Sn minus 1, k minus 1 plus k times Sn minus 1, k. So in particular, Sn, 3 equals Sn minus 1, 2 plus 3 times Sn minus 1, 3. In other words, an is equal to 3 times an minus 1 plus Sn minus 1, 2, but this we just computed, so we get 3an minus 1 plus 2 to the power n minus 2 minus 1. And this is a non-homogeneous linear recurrence. The characteristic polynomial of this recurrence is x minus 3, and so the general solution to the corresponding homogeneous recurrence is alpha times 3 to the power n for some alpha. Let us look for a particular solution to this non-homogeneous recurrence in the form beta times 2 to the power n plus gamma. So the additional term here is a power of 2 minus some constant. So we look for a particular solution in the form beta times a power of 2 plus some constant. If we plug this into the recurrence, we get the equation beta times 2 to the power n plus gamma is equal to 3 beta times 2 to the power n minus 1 plus 3 gamma plus 2 to the power n minus 2 minus 1. And this we can rewrite as 6 beta minus 4 beta plus 1 times 2 to the power n minus 2 equals to 1 minus 2 gamma. And for gamma equal 1/2 and beta equal minus 1/2, both sides are 0, and so we get the equality. Therefore, minus 2 to the power n minus 1 plus 1/2 is a particular solution for the non-homogeneous recurrence. And hence the general solution for the non-homogeneous recurrence is given by alpha times 3 to the power n minus 2 to the power n minus 1 plus 1/2. To determine alpha, let us recall that A3 is equal to 1. So for n equals 3, we get that 1 is equal to alpha times 3 to the power 3 minus 2 to the power 2 plus 1/2. And this gives alpha equals 1 divided by 6. So the answer is an is equal to 1 divided by 6 times 3 to the power n minus 2 to the power n minus 1 plus 1/2. And this we can rewrite. So the Stirling number Sn, 3 of the second kind equals 1/2 times 3 to the power n minus 1 minus 2 to the power n plus 1. And this is true for all n greater than or equal to 3. And this is the answer to the second part of our problem. Problem 4. An examination consists of 20 multiple-choice questions. Each question has 4 choices for an answer, only one of which is correct. To pass the examination, one has to answer at least 14 questions correctly. What is the probability to pass the examination by randomly choosing one answer for each question? Solution. Since we have 20 questions and 4 answers for each question, by the rule of product there are exactly 4 to the power 20 different ways to answer all the questions. For any k between 0 and 20, let us compute the number of ways to answer all questions such that exactly k answers are correct. So we can choose the questions which we answer correctly in 20 choose k different ways. And for those questions we have the unique answer. And for the remaining 20 minus k questions, we need to choose one of 3 incorrect answers. By the rule of product, we can do this in 3 to the power 20 minus k different ways. Therefore, there are 20 choose k times 3 to the power 20 minus k ways to answer all questions on the examination such that exactly k answers are correct. And now, if we add this up over all k from 14 to 20, we get the number of ways to answer all questions such that at least 14 answers are correct. So that's sum over all k from 14 to 20, 20 choose k times 3 to the power 20 minus k. And now we divide one by the other. So the probability to pass the examination by randomly choosing the answers for each question, so one answer for each question, equals the following fraction. The denominator is 4 to the power 20, and the numerator is the sum over all k from 14 to 20, 20 choose k times 3 to the power 20 minus k. One can approximate this as a real number, so the approximate value of this expression is 0.000056. So the probability to pass such an examination by randomly choosing the answers is quite small. Problem 5. A classroom consists of 10 desks with 2 places at each desk. 6 boys and 4 girls are randomly seated in this classroom. Let X be the random event that each boy sits next to a boy at a desk. Let Y be the random event that each girl sits next to a girl at a desk. Determine whether X and Y are independent. Solution. Recall that two events x and y are independent, by definition, if and only if the probability of x intersection with y is equal to the probability of x times the probability of y. The probability of x intersection with y equals the cardinality of x intersection with y divided by the cardinality of omega. Omega is a sample space. The probability of x equals the cardinality of x divided by the cardinality of omega, and the probability of y equals the cardinality of y divided by the cardinality of omega. And so our equation for independence can be rewritten as the cardinality of x intersection with y divided by the cardinality of omega equals the cardinality of x divided by the cardinality of omega times the cardinality of y divided by the cardinality of omega. And we can rewrite this as the cardinality of x intersection with y times the cardinality of omega equals the cardinality of x times the cardinality of y. So to answer our problem, we need to compute all these four cardinalities. Let us start with the cardinality of omega. So for this, we need to determine in how many ways 10 people can be seated in a classroom which has 10 desks and each desk has 2 places. We have 10 people and 20 places. The first person can be seated in 20 different ways, the second one in 19 ways, and so on. So from the rule of product, the cardinality of omega is equal to 20 times 19 times 18 times and so on times 11, which we can shortly write as 20 factorial divided by 10 factorial. That's the cardinality of omega. Now the cardinality of x. If the seating is such that each boy sits next to a boy at a desk, they occupy 3 desks, because there are 6 boys. We can choose these 3 desks out of 10 in 10 choose 3 different ways. We can place the 6 boys at the corresponding 6 places, so 3 desks, 2 places at each desk, in 6 factorial different ways. What remains is to place 4 girls at the remaining 14 places with no restrictions. And the same argument as for omega gives that the girls can be seated in 14 factorial divided by 10 factorial different ways. Using the rule of product, it follows that the cardinality of x equals 10 choose 3 times 6 factorial times 14 factorial divided by 10 factorial. Similarly, we can determine the cardinality of y. So, if we place girls such that a girl sits next to a girl, they occupy 2 desks. We can choose these desks in 10 choose 2 different ways, and we can place 4 girls at the 4 seats which we have chosen in 4 factorial different ways. What remains is 6 boys, 16 places, no restrictions. So the same argument as for x or for omega gives that boys can be placed in 16 factorial divided by 10 factorial different ways. And using the rule of product, we have that the cardinality of y equals 10 choose 2 times 4 factorial times 16 factorial divided by 10 factorial. And finally, let us determine the cardinality of x intersection with y. From the computation of the cardinality of x, the 3 desks for boys can be chosen in 10 choose 3 different ways. After that, the 2 desks for girls can be chosen in 7 choose 2 different ways. We can place 6 boys at their seats in 6 factorial different ways, and we can place 4 girls at their seats in 4 factorial different ways. From the rule of product, it follows that the cardinality of the intersection of x and y equals 10 choose 3 times 7 choose 2 times 6 factorial times 4 factorial. And now we have the equality which we need to check to determine whether x and y are independent. So the left-hand side is the cardinality of the intersection times the cardinality of omega. So this is equal to 10 choose 3 times 7 choose 2 times 6 factorial times 4 factorial times 20 factorial divided by 10 factorial. The right-hand side is the cardinality of x times the cardinality of y. This is 10 choose 3 times 6 factorial times 14 factorial divided by 10 factorial times 10 choose 2 times 4 factorial times 16 factorial divided by 10 factorial. First, we delete the obvious common factors, which are 10 choose 3 on both sides, then 6 factorial and 4 factorial. So what remains is on the left-hand side 7 choose 2 times 20 factorial, and on the right-hand side 10 choose 2 times 14 factorial times 16 factorial divided by 10 factorial. Now we can write binomial coefficients using factorial, so the left-hand side is 7 factorial times 20 factorial divided by 2 factorial times 5 factorial, and the right-hand side will have in the numerator 14 factorial times 10 factorial times 16 factorial, and in the denominator 10 factorial, 2 factorial, and 8 factorial. So on the right-hand side we cancel 10 factorial in the numerator and denominator, and then on both sides we have 2 factorial in the denominator we can cancel, and then we move 8 factorial from the denominator on the right-hand side to the numerator on the left-hand side, and similarly 5 factorial from the left to the right. And so we have the expression 7 factorial, 20 factorial, and 8 factorial on the left-hand side, and 14 factorial, 5 factorial, and 16 factorial on the right-hand side. But here we now see that, for example, the prime number 17 is a part of 20 factorial, so it divides the left-hand side, but it doesn't appear on the right-hand side. So this equality cannot hold, it is false. And this proves that the random events x and y are not independent. Some additional problems and questions at the end. Problem question 1. Find the generating function for the number of partitions of a non-negative integer n into distinct even parts. Problem question 2. Find a closed formula for Sn, 4 where n greater than or equal to 4. Problem question 3. A fair coin is tossed 10 times. Let x be the event that the first coin outputs heads. Let y be the event that the total number of heads is even. Are x and y independent? Problem question 4. 6 friends randomly take seats around a round table. What is the probability that Alice and Bob, 2 out of these 6 friends, sit next to each other? And problem question 5. 8 people are randomly divided into 2 teams of 4. What is the probability that Alice and Bob, 2 out of these 8 people, are in the same team? Thank you very much and see you next time.